Hi there, and my congrats for your patience and stamina for joining me again and listening my first lecture regarding the interference effects. And now I would want to congratulate you that, okay, you're already this way up or down in our list of contents on the course, so you're almost there. And here, so that we learned in chapter 7 regarding superposition of fields, and now in chapter 8 we are essentially just going through the same piece of mathematics, and then in chapter 9 we will be extending our discussion into a continuous variables, so essentially continuous distribution of fields that we are summing together, so that that will be the main difference between the interference effects and diffraction effects. And then I will speak a little bit about the overall table of contents for the upcoming lectures I will be handling to you. So this lecture, of course, once I get started, I will be speaking about the conditions for interference. So I will introduce to you again the main assumptions and approximations we take when we take our treatment in this chapter, and we will calculate the superposition fields. We will calculate the corresponding irradiance distribution and find out that indeed it's also the polarization of light that is actually quite important when we're looking at the interference fringes and their formation. And I will be speaking about the de Moivre's formula slightly, which is a very useful equation when we try to simplify equations that are dealing with complex numbers. So exponential notation of complex numbers and sines and cosines. And at the end of this lecture, we will be pointing out that interference to happen between fields, the fields must be coherent. So consequently, we need to speak a little bit more about the coherence. And I will be speaking about two different kinds of coherence. So mainly I will be teaching you a main difference between temporal coherence and spatial coherence. So that will be what I will be teaching you once I get started, by providing you first a kind of table of contents overall picture of what we will be learning in this chapter 8. So this we have already covered, and soon will be covered more extensively. And then after that lecture, I will be speaking about the two different classes between interferometers. So I will be speaking first in 8.2 regarding what in general is an interferometer as an instrument, and we want to understand how they behave. So I will be speaking a little bit about them, and then I will provide the way to divide or classify interferometers into two different classes, so mainly wavefront splitting interferometers and amplitude splitting interferometers. And there in 8.2, I will be considering also an example of Young's double slit experiment. Then in lecture 8.3, I will be speaking about amplitude splitting interferometers. So here in particular, we will be looking into thin film structures. They are, I guess, the easiest configuration we can imagine for these kind of interferometers, and they are also of very high practical and scientific relevance. So in many places in nature, we can actually find thin film structures, and then their strange, peculiar coloration that is being provided when we have that kind of structures. So this is a very useful thing for the future for us to understand what happens in terms of mathematics when we have these kind of structures. And then in lecture regarding Michelson interferometer, as the name suggests, we will go through the configuration of a Michelson interferometer, and we will derive the conditions for the phase differences when we have the different arms in the interferometer. And in the second part, I will provide you hopefully a practical example how that kind of instrumentation can be also used to do spectroscopy. So essentially, I will be speaking a little bit about the Fourier transform magic that can be done with the Michelson interferometer. So again, I must warn you with the label that the good stuff on the way, especially in chapter and lecture 8.4 regarding Michelson interferometers, since Fourier transforms are being mentioned here. So in then lecture regarding multiple beam interference, so here we will be essentially generalizing our treatment of thin films, but now into a scenario where we actually have highly reflecting interfaces. And these, of course, will be something that doesn't take place in nature that often anymore, so that they then we are approaching more and more engineering sciences, but nevertheless multiple beam interference is highly useful, and we will show to you in this chapter that they were actually able to make a so-called Fabry-Perot devices, so Fabry-Perot interferometers and ethalons. So I will be speaking about the kind of main implications regarding that applications. So we will go through the math, how that kind of components will behave, how light behaves in that kind of situation when we actually have two interfaces that start to be now highly reflecting, and speak about the implications in terms of engineering. And then in sixth lecture, I will be speaking more broadly about these Fabry-Perot instrumentation. So essentially thin film structures where the interfaces are highly reflecting. So I will be speaking about the interferometers, Fabry-Perot interferometers, and Fabry-Perot ethalons, or just shortly ethalons structures. And then finally, I will be ending my chapter by speaking a little bit about the Fabry-Perot structures from their spectral properties point of view. So if it would be, for example, utilizing these for spectroscopy, or we would want to use our ethalon to specify, for example, the wavelength of our laser system, that we would have a really narrow and well-defined output laser, then we will introduce the main parameters and concepts that you would understand when somebody would be speaking to you about that kind of application with the Fabry-Perot structures. So this will be my outline, and this was my outline for these lectures that we will be speaking shortly to you regarding interference effects. But now I will start my actual lecture, so I will go with the conditions for interference, and I already provide a kind of rough outline for this lecture before I got started with the previous introduction on the actual main whole chapter. So let's start with the very general notions regarding interference. And what this is about, of course, is essentially that we have waves and they are being summed together. So we're actually forming a superposition of waves, and then something happens. We have interference phenomena, or we may have diffraction phenomena, and this is the main point. And here in this chapter, we will really focus only on the interference phenomena, as the name suggests. But in a way, same math could also be applied for the next chapter regarding diffraction phenomena. The main difference here between interference and diffraction is that in interference phenomena, we are thinking of superposition of fields when we have a finite number of waves that we are summing together. And when we are thinking of diffraction effects, it's rather a continuous distribution of waves that we are summing together that forms the superposition of fields. So here I'm trying to color code you a little bit of help what I'm trying to say here. So interference phenomena, we actually have a discrete number of waves that we are summing together. So in essence, there's a finite number of waves that we are summing together. And here we will be starting our description by just assuming that we have two plane waves. So they just are nicely defined with a single wave vector propagating in some direction in a 3D space. And they are also monochromatic, just meaning that there's also a single well-defined frequency at which the plane waves are being oscillating. So monochromatic as in a time harmonic. So then essentially we have two fields, and now I have the notation tilde, meaning here that I'm describing these guys in the time domain. And this first field will be of a form that we have a amplitude A1, and this is a vectorial quantity, so that we have the polarization involved here. Please, more on this later, why polarization is now actually an important thing. Then we have the initial phase, epsilon y there inside the exponent argument, and then we have the plane wave component K1R dot product telling us in which direction the plane wave is propagating, and then we have the angular frequency time dependence. So essentially a time harmonic field propagating in direction defined by the K1 wave vector. And similarly, the second field is of exactly the same formula, so that we have a vectorial amplitude and all the rest of the terms are known. So this is what we start with, and we now want to calculate the sum wave, so known as the superposition of these waves. And we can easily calculate this, no trouble here. So mathematically, we are just summing the waves together. And so we have these equations that we are summing together, and there's nothing strange about this. We can already take out the time harmonic time dependence out of these both terms, so that what's left is then inside the parentheses the spatially varying parts, and then we have the time harmonic time dependence there as a common term. So here, essentially, what we have inside the parentheses, that's the spatial dependent part, and that's the kind of main thing that we should now try to disentangle how it actually looks like. And of course, we're interested in calculating the irradiance pattern, so what kind of interference patterns are being formed subsequently, because that's in fact what we would see with a detector or our eyes. So essentially, this is of interest here. And the irradiance, of course, it's proportional to the modulus square of the total field. So essentially, we can calculate this quite easily by just taking the dot product between the sum wave E with its complex conjugate, so E star. So essentially here, just what this means is that we would have the first superposition of fields, and then we multiply that with the complex conjugate of this total field. And then, of course, we know already what comes out is that we have the first two terms. So these would correspond to essentially the irradiances of individual waves. And then we have the interference term, which is caused basically by the interference. So we have two waves, and when things are right, we're actually seeing interference effects, and these are caused by these latter two terms. And where we have the complex conjugates of the respective fields. So let's now look more carefully into those two interference terms. And please note, we now have actually vectorial forms for them, so that we can actually finally say something smart about the requirement for polarization states to see actually interference. So we have the first interference term, so E1 with the dot product of E2 star. And this, of course, will be a form that we have the complex amplitude and vectorial amplitude of the first field, A1 dot product with the A2 star. And then we have the initial phases here. And since we have the complex conjugate of the second field here, so we have the minus sign in the initial phase of this second field. And then we have the spatially varying part for the for the plane wave contributions. And here again, we must reverse the sign for the K2, since we have the complex conjugation of the second field, like this guy in here. And similarly, we can write the second interference term, so now E1 star times the E2, and this is quite similar looking entity, so now we just do the complex conjugation on the first field term. And these are now nice, because this is actually like the general way of doing things. So we have vector valued fields, and now we really see that for example, the interference terms, they would vanish when we would happen to have orthogonal polarizations, because then those terms would vanish. So essentially, mathematically, what this would look like is that we would calculate the irradiance, which is proportional to the modulo square of the total field. We have the separate irradiances, and then we have these interference terms, as we already noticed. And if these would be zero, what would be left is that we would not have actual interference pattern forming, but rather just a summation of the irradiance patterns of the individual fields. And this is something that would not look like interference at all. And this would take place if we would happen to have orthogonal polarization states for the fields E1 and E2. Because essentially then we would have this A1 times A2 star. This would be 0. And similarly, A1 star times A2 would be 0. So this is basically what tells us that there's in fact this kind of requirement for interference fringes to be present. So we actually really need right kind of polarization. An example polarization state would be, for example, that we would have a linear polarization polarized along x direction. So A1 would be essentially, for example, like a unit vector pointing along x direction. And then A2 would be, for example, a unit vector pointing in the y direction. Or they could have different amplitudes here. Sorry, there's a typo there in the notation. We should have a scalar valued A0 here, of course. And this as a notation doesn't really make much sense. And of course, the amplitudes could be whatever as long as the x and y point in orthogonal directions, so that it doesn't really matter what are the actual amplitudes of the fields. We just don't see interference when the polarization is orthogonal between the two different fields. So that's it. And this is a nice thing to know, that because sometimes this is actually what must be considered and what must be right for interference effects to actually occur. So let's now proceed. And for the simplicity, let's just assume that the polarizations of the interfering waves, that they are identical. And basically we can assume that they are parallel. And in this case, the math is being simplified. So for example, the two terms, they are equal since the polarizations are identical. And essentially we can write these in a scalar form. So we have A1 times A2, and that's simple as that. And now we can write the superposition terms easily in a scalar form, so that the irradiance pattern of interest, that's still proportional to the modulo square of the total field. And now we have the interference term, the individual terms of the irradiance distributions of the individual fields. And then we have the interference term that is of a form 2 times A1 times A2 times cosine of delta, where delta is a phase difference between the two waves. And of course, this is given by the difference between the initial phases, so epsilon 1 minus epsilon 2, and then we have a spatially dependent phase term difference, so k1 minus k2 with the dot product of r, that gives me a phase difference. So this is basically what gives me either a constructive interference or destructive interference or something in between. And now we can write the equation entirely in terms of the irradiances. So essentially the first term, A1 squared, that's essentially the irradiance of the first field. And the second term here, this guy is essentially the irradiance of the first field, and then this guy is the irradiance of the second field. And then we have this second term, and that we can also write in terms of irradiances. So we just take the square roots of these to make things explicit. So this is how things look like, and this is quite nice. I'm now confused why I'm extending the square root into here. I would say that it must only be in here, so that the phase term would not be inside the square root. So my apologies for this typo. Should not be the case that it's being extended now into here. I will correct that into your actual notes that you will be getting from the Moodle. So irradiances, if they are equal, and this is what we assumed, E1 equals E2, we can just denote these as being E naught. And then the total irradiance pattern, we can simply write that it's the 2 times E naught plus 2 times I naught times cosine of theta. And now we can simplify terms, so it's basically 2 times I inside a parenthesis of a term depending on the phase difference, so 1 plus cosine of the delta. And then this can be simplified into a form 4 times I naught times cosine squared of delta over 2. And this is nice. Here we have utilized the Moivre's formula. Please, future educators and teachers and just science nerds, please note this is highly useful formula worth memorizing. So a complex number, we can write it either in a polar form, so it's r, the length of my complex number in the complex plane, times cosine theta plus I sine theta. And now using the Moivre's formula, we can write that the power, nth power of this complex number Zn is actually r, the length, to the power of n, times cosine n times the angle plus I times sine of n times the angle theta in the complex plane. So this is highly useful, and now we can really just consider only the real part of the complex number z in our derivation. So essentially z is the complex valued number, and if the length of the complex number is 1, essentially the r equals 1, then we only need to look into the real part. So if you look into the z squared, this is essentially cosine squared of theta plus I squared times sine squared theta plus 2 times I times cosine theta sine theta. So essentially we can just mindlessly calculate the second power, and this is what we will get out. And this we can simplify. So this is essentially now that we take use of the Moivre's formula, so that what we have on the other side is that we have cosine 2 times of theta. And then on the other side, we have cosine theta squared minus sine squared of theta. So here we have taken use of the fact that the cosine squared theta plus sine squared theta equals 1. And this we can use to simplify things further in the next slide. So essentially, like here, if you look only at the real parts, so then we do not need to consider this term and this term. Oh, sorry, definitely we need to consider this term, that this is the minus sine theta here. But if you only look at the real part of this, by taking use of the de Moivre's formula and recalling that the length equals 1, we get cosine 2 theta out here into the left-hand side by just taking use of the de Moivre's formula on z squared. And then what we have here, we just have this term, and this is the imaginary part. So this we can scrap if you're only looking at the real parts. And now we take use of the trigonometric identity on the right-hand side. And what we get here is that we have a cosine 2 theta equals minus 1 plus 2 times cosine squared of theta. So this is where we have taken use of this trigonometric identity here to simplify or get rid of the sine squared term. And then basically we have taken this use of this. And now finally what we get is that we can write the terms, we can move the ones to the other side so that we have this equality. And now delta here, we can equate that if that is 2 times theta, then we can take use of this to actually simplify and get into this guy here. So please note what we have inside the parentheses, 1 plus cosine of delta. This now essentially looks almost, oops, sorry about that. I will now try to get rid of that. So essentially I have this guy here and I have this here. So now I'm just replacing 2 theta with the delta. So I get this here, and then I'm replacing this theta with the delta over 2, and I get this equality here. So that's what we got out. And then we were showing that the de Moivre's formula is actually highly useful. Nice thing. So we have the equation for the total irradiance. And of course, from this, we can easily see the conditions when we have a constructive interference and when we have destructive interference. So the maxima takes place. So when we have constructive interference, when the phase difference delta equals a 2 pi and a integer of that. So n here is an integer number. And we have destructive interference, so that the phase difference delta is a 2 pi n plus p pi, so basically an integer of pi difference. And now we have really seen what we need for interference effects to take place. So we must have the right kind of polarization state, and then we must have a right phase difference between the two fields we are summing together. And once we have them in place, we can actually calculate how things look like. And in addition to this is that we have really implicitly assumed that the waves or light distributions we're considering, they are mutually exactly in coherence. And this basically means that the phases of the waves correlate exactly in all given instances of time. So please check the final lecture I had on chapter 7 regarding the kind of very basics of coherence. So this is essentially the kind of intrinsic requirement that we also need for interference effects to take place, so that the fields must be also coherent with respect to each other. And that just essentially means that there's always a phase correlation between the phases. And in a way, this of course makes sense. We are interested in calculating the phase difference between the fields. So of course, we should actually be able to use this mathematics that the phases are actually correlated. And if the two fields are not coherent, then we should actually extend our treatment into statistical treatment, so that we should actually consider some kind of time varying quantities where the phases would be randomly flipping and things would become quickly quite awful. But we were happy to know that we were on an introductory level of courses, so that we do not need to worry about that kind of complication for the math. And now, since we are speaking about coherence, let's briefly speak a little bit more. So let me introduce to you two different notions regarding coherence of light. So what kind of coherence properties we have and how we can understand them to manifest themselves. So earlier we have really focused on so-called temporal coherence of light, or light sources, and this is also known as a longitudinal coherence. And basically what this means, or one way of understanding what is a temporal coherence, is that we are looking at two waves that are being radiated by a source, and they propagate at given optical distances. So the other wave propagates a distance of s1. So essentially that is the t1 times this wave has been propagating from the source times speed of light c. And the second wave we are letting to interfere with the first wave has propagated a distance of s2, where essentially this is equal to the time t2, the time it took this part of a wave to propagate from the source into the given observation point, and t2 times c gives me the distance. So essentially, these two waves propagate from a source, and they are being like guided into a single observation point, and there they are being interfering. So this is essentially like the schematically what's happening in temporal coherence. So some fields are coming together, they are put together, and depending on the kind of optical path length they have propagated, their relative phases may be different, and then we either see interference or not. And then on top of that, when the coherence time, so that the temporal coherence either is good enough, we actually do see interference, but when we are actually like increasing the distance difference between the waves that have been propagating, we're starting to lose temporal coherence, and then we are no longer seeing interference in here again anymore. So this is what starts happening with respect to temporal coherence of sources. So waves essentially they interfere if their mutual time difference is smaller than the coherence time of my source. So essentially, when the time difference is smaller than coherence time tau c, then we will see interference effects. And mathematically, this just basically means that we take the modulus of the time difference, so t1 minus t2. This must be smaller number than the coherence time tau c of my source. And equally well, I could just define this instead using the optical path difference. So I could use the coherence length as a concept or way to quantify or estimate do I see interference. So essentially, I could equally well look at the distances and their differences. So essentially, the modulus of S1 minus S2, and this should be smaller than LC, where LC is the coherence length given by the speed of light c times the coherence time tau c. So these are the two ways of looking at things. And as long as the temporal separation between the two portions of the wave, well, like the temporal separation is smaller than the coherence time of my source, I will see interference effects. But of course, when we just increase the separation in time, then we are actually starting to lose our coherence, and thus we don't see interference fringes anymore. And another kind of concept that sometimes arises when we're looking at the coherence properties is a so-called spatial coherence, and this is also known as a transverse coherence. And now in this case, we are looking at a mutual coherence of two different points of the same phase front. So essentially, we are looking at the two different locations, or we seemingly are looking at the two different locations, R1 and R2, and we are interested in letting these different portions of the same phase front to interfere. And now we are interested in seeing, do we still see interference here or do we not? And sometimes, like for example, when we have many modes in our laser source, we are losing the transverse coherence, so that then when we are letting a field in the R2 to interfere with a location in R1, and when this separation is large enough, they do not anymore interfere. And this is essentially due to a fact that we are losing the transverse coherence due to a fact that our light distribution actually consists of many different spatial modes, breaking our coherence essentially. So we are looking at the fields of the investigated points, so fields at R1 and R2, and we bring them into a single observation point, and now we want to see, do we see interference or not? And we see interference if the distance is smaller than a so-called coherence width, here denoted with a WC. So essentially, when the distance or a difference between R2 and R2, so modulus of R1 minus R2 is smaller than the coherence width, is that then we start actually seeing interference effects. So these are the two different classes or types in terms of coherence. And for you, I guess it's good to know that there is also the spatial coherence, especially from the point of view if somebody is speaking to you about a longitudinal coherence, you know why it's called that, so that there's also something known as a transverse coherence. But in what follows, by far the more interesting and important will be the temporal coherence, so essentially the longitudinal coherence. So I would say for now, for an introductory level treatment of interference and coherence, you can pretty much forget spatial coherence and you can only consider temporal coherence, and that will be adequate in our treatment what follows. And now I'm at the end of this lecture. I thank you for listening to me, and I hope you had a nice time. And soon, please join me again when I will be speaking about the wavefront splitting interferometers. Okay, thanks and bye-bye.